Welcome to today's webinar. Today we will show you how you can model and design a timber arc structure in Rfem 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, technical content of the website, the German and English webinars, customer projects, newsletters, and so on. I will be the moderator today and I will answer your questions together with Gerhard Rehm. The presenter will be Benaral Chabani. He works also in the marketing team, is also responsible for technical marketing. He prepared the webinar together with me and the timber design experts, Gerhard Rehm and Bastian Kuhn. Gerhard, is responsible for the development of the timber design add-on, and he works also in the customer support team. Okay, I show you how you can ask questions, at least for the attendees who participate the first time. I switched off my webcam that you can see the full screen. If you have a question, just press the button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Benaral. Benaral, it's your turn.
Thank you, Andreas, for the introduction. I would also like to welcome you all to our webinar today. I would like to start with the agenda for today. At first, we will start by modeling the round arch hall in our program Rfem 6. As second, we will continue with the load input and the combinations. And at the end of it, we will see the design of the timber components according to Eurocode 5. To proceed with our project, I would like to go to our program Rfem 6. Here I need to create a new model. Which I will name it Round Arch Hall. The add-ons that we will need today are the timber design and also the structure stability. We also need to pick our standards. We will need the European standards for timber, also with the German National Annex. We can continue by tipping OK. There is a possibility that for the latest projects that we've done in Rfem 6, you probably would have here the materials or also the sections that you used before. To delete them, you can just go to the basic objects and say delete all basic objects. In this way, everything is deleted and we can continue with the model of our hall. First, I will need to draw here an arc. To do that, I will pick here an arc via 3 nodes. Our hall needs to have a height from 5 meters and also a 20 meters wingspan. We have modeled our arc. Now we need to have a member from it. Of course, we need to select a new section and also a new material. We will search here for the region in our library for European Union and a material type of timber. For our round arch hall, we would need a glue laminated timber, GL28C. As a section type, we will choose Massive 1 for us to be able to just write our geometry. In this case, we need the geometry from 200 millimeters times 480 millimeters. Say apply and OK. And we can see that we have our truss. Of course, our truss needs also the hinge nodal support. We just need to select the nodes and we will have our nodal support modeled. We can also see that they are a bit too small for the model to look also better, and also for us to be able to see it in a better way. We can just make them a bit bigger. That would also look a bit better, and also like we would have a better eyesight to the program. As next, we want to divide our truss in an intermediate nodes. We will divide it in 5 intermediate nodes. We need the nodes for the coupling. They are very important because the coupling rods should be located at these points where the nodes would be, and we can copy the truss. When we will copy the truss, we will also create the coupling rods. But we'll proceed here firstly with OK. We'll see that our member is divided in 5 nodes, 5 intermediate nodes. Before we copy it, we firstly need to create a member set. Here we don't need to do anything, we just press OK, and we can see that we already created a new member set. Now we can be ready for us to copy our member. To do that, we will need to check here, create copy. And for our round arch hall, we will need 5 number of copies. But as we said, here where the nodes are, we will need to have also the couplings. Instead of modeling each one of them, we can just proceed here at the menu numbering and options and check here step links. And then we say here link nodes with line and also nodes with the member. Of course, here we need to also find another type of section. We go to the sections, but firstly we need to choose our member type as truss. We can add a new section here and say for the truss I need a geometry of 120 millimeters times 120 millimeters. We'll press OK. The material is also the same, so we don't need to change it. We just can proceed with OK. And we say that I want to have my copies in Y direction every 5 meters. We'll press OK, and then we will see that our round arched hull would be modeled. Of course, the trusses here at the bottom, we don't need them, but I think it's faster this way for us just to delete them, so we can just delete them. Of course, we could have also before deselect the nodes here, but yeah, that would be just unnotted work. We can see that our hull is partially modeled. The next thing to do is to model here the beams that will serve as gable support. To do that, I will need to find another section, but this time not anymore as a truss, but as a normal beam. Of course, for our gable supports, we will need to choose a new section, which will have the geometry of 100 millimeters times 200 millimeters. We can press here OK to proceed. The material of the gable supports can still be the same, so we don't need to change anything here. I will first start to model them as shorter beams, and then later I will extend them until the next member. Of course, they also need their personal hinged nodal support. We can select the nodes and proceed with OK. To extend the gable supports until the next member, we need to select all three of them. We can find here extend or trim member until through the next member or line. We can just proceed here with OK, and we can see that our gable supports are extended to the next member. We also need to turn the gable supports. We need to rotate them in a 90 degrees angle. That way the major axis will be in the longitudinal direction. To do that, we need to edit all three of them. We will go to the sections menu, and here we can see a part that says member rotation. Here we can just type rotation angle of 90 degrees and then press OK. We can see that our gable supports are rotated in a 90 degrees angle. At the top, the gable support should be connected with hinges that also can be moved vertically. Later, the gable supports can be removed for example, when the hull needs to be extended. To do that, we should edit all three of them. And we need to check here the menu hinges. The hinges would be needed at the member end, so we will choose a new one. Therefore, we need a moment hinge around the longitudinal axis, which essentially doesn't impose any vertical loads. We will proceed here with OK. And then we can see that we have already modeled our hinges. Of course, we need the gable supports also for the other part, so we just can copy them. We will select everything that we need to copy and go to the menu, Move or Copy. We'll select here the menu of Create, Copy, and we will need just one copy. Here, you need to also be careful because for the trusses, we also needed the couplings, and probably there is a possibility that this option is still on, so we just need to turn it off. In our case, it isn't like that. We can choose our displacement vector just by choosing 2 points on our model. The first point that I will choose would be the point here, the original, and the next point where I want the things to be copied. We'll say here OK, and then we can see that the gable supports are also modeled for the other side. The next thing I want to do is I want the connecting rods to align along the top edge of the truss so that each rod has a different angle. To do that, I need to align them toward the center of this arc, of this truss. How does this work? We can find it now. In our example, we can see the middle point of this arc. But if in your model you cannot see it, you can just go to the display navigator and search here for lines. And here you would see a menu that says center point. You can just turn this on, and then you will see this small signs. Here, I just need to put a node as a helping node. And then I also need to select all the rods. You can do it in a lot of ways, just by selecting here or going to the views by visibilities. We can activate them, and then we can search for members by section. We know that our rods have a section of 100 millimeters times 120 millimeters times 120 millimeters. So we can just see them. We can select everything and then deactivate the visibilities. Now we can edit all of them. And at the menu member rotation, as a rotation type, I don't need an angle anymore, but I need a help node. I think we know that which node are we going to select. And in the plane X until Z. We'll say here OK. And then we will see that our rods have now an angle, a different angle from one another. They are also the same way as I wanted them to have. Now, the thing that I need to do is the bracing. For that, I will create another section. As a member type, I will use tensions. Here, I also need to find another section and also another material. Firstly, I will choose the next material. I will need a material for steel. Here we go firstly to the library, and as material type, I will search for steel. I can also type here S235. I can press here OK, and now I need to look for a new section. For our bracing, I would need a round. As a section type, I would need a massive one, so I can give the diametry by myself, and I will also need a round section. We'll need a diametry from 16 millimeters. We can proceed here with OK. And then we can start to model it. For it to be easier for us, I can put our model into a wireframe model, so I can see every node and every line that I also need to select. Modeling the bracing can be done like this, or you can draw just one of them and then you can mirror the other side, or with a rotation. There is a lot of ways how to draw them. In our example, I will draw them until here, and then I want to mirror them for also the other side. To select all of them, I just click at the blue member representatives, and then I will go to the menu mirror. I will also need a copy from it and select the plane Y, Z. I will also need to pick a point here. which would be the node here, and just press OK. We can see that our round arch hull, it's fully modeled. Now we come to the second part of our webinar, which is also the last input. To proceed with that, I will firstly need to model at the gable supports 2 load transfer areas, which will help with the load transfer. They are probably the biggest advantage that we have today in Rfem 6 and that we also use in our model. Because of the roof construction, there are triangular and trapezoidal loads that apply to the gable supports. Without the load transfer area, we would have to apply the triangular and other types of loads individually. That would be a waste of time, and it would also be a lot harder than just putting it with the load transfer. First of all, I will need to draw here a line which would help me and serve as the borders of the load transfer area. Second, I can just go to the menu here and select boundary. As a stiffness type, I will need a load transfer, and as if you can see, I cannot say that I want a thickness or a material because it's a surface that it's in the reality not there. It's just there in our program to help us with the load transfer. We will continue with OK, and then we will select our boundaries. We can see that we modeled our first load transfer area, and now we proceed with the second one. Now we also have the second one. Our hull tenses in x-axis. That's why we also need to go to the load transfer and select the category as a load transfer direction just in X stripes. That means that the surface is cut along the local axis into many surface stripes. The local axis, we can see if you just put the mouse near the load transfer, and then you can see the the axis. The same thing we also need to do for the next load transfer area, and then we can proceed with OK. As the first load, I will need here dead load and also the roof structure. I figured that here from truss to truss there would be trapezoidal profiles like sandwiches with insulation on top and a foil roof. I assumed it will weigh like 30 kilograms. Of course, the dead load can vary from hull to hull. I would need a new member set load and type here 1.5 kilonewtons per meter. As a load direction, it's global in Z on true length. And now I just need to select my member sets. We will press OK, and then we can see our load being generated. Of course, at the gable supports, it will be the half of the load. So we go and select a new member set load and put just the half of it. We will proceed with OK. Then we will be done with the dead load and the roof structure load. To proceed with the snow load, I would like to go to my presentation. The snow load will proceed according to DIN 1999-1-3, section 5.3.5 for the barrel roofs. These standards specify two variants that must be considered: the unblown snow and the drifted snow load. We must represent these two variants using two load cases. Firstly, the snow load as a distributed load, and also the drifted snow load as a double triangular load. I think that the values, you can understand what they mean. I cannot show the standards here because of copyright, but we have here the form coefficient, the characteristic snow load, and also the influence width, that for the unblown snow equals 3.4 kilonewton per meter as a member set load. For the drifted snow, of course, we have different form coefficients. Here we have a 2.0, which will equal as an 8.5 kilonewtons per meter, and also as a second part, the half of it. To proceed with the snow load, I will also go again to the program and select here new load case. As an action category, I will need to choose here snow and consider with OK. Of course, I will need a new member set load. And then type here 3.4 kilonewtons per meter. Now, as a load direction, according to standards, I need to choose a load direction global in Z on projected length. And now we just need to select our members. We can proceed here with OK, apply and next, and then we can see that our load for the main trusses is modeled. And then say here that at the gable supports, I have just the half of it. We also select the gable supports and then proceed with OK. This way we are done with the unblown snow load. Now we can proceed with a new snow case, which is the drifted load. Of course, I need to put here a new load case, which I will name drifted snow load. As an action category, it can stay this way. I don't need to change it. I just need to proceed with OK. And then select here once again, new member set load. We said that here we have a double triangular load. So to be able to put this type of load into our program, we need to choose as a load distribution varying, and then we can just type our parameters by ourselves. Then we start here at 0 meters, which we also have a force of 0 kilonewton. 5 meters, which will be the first value of our load. Here we have the half of it. Also, just from the parameters, we can just a bit imagine how our load will look like. That would look just like a triangular here, where it goes up at 8.5 and then goes also down at 0, then up again, and then now at 20 meters, which is our span length, would go again to 0. Now we just need to choose once again the members that we need the loads on. We can proceed here with apply and next and see our load generated. Of course, at the gable trusses, we need the half of it. We can proceed here with OK, and yet we are done with the drifted snow load. As next, it would be the wind load. For that, I need to also go again to my PowerPoint. For the wind load on truss, like crosswise, we will have a load distribution according to DIN 1991-1-4, section 7.2.8 for curved roofs and domes, which will tell us to split our truss in 3 different areas, area A, area B, and area C. For each area, we will have different CP values, starting with a 0.4 for the first area, 0.95 for the second area, and also 0.4 for the last area. This area is 1/4 of the length of one of our trusses, and here is also the rest. 1/4 of it will be applied as a weak pressure, and also the rest as a wind draft. Therefore, we will look at our results that we have here as 1.3 kilonewtons per meter, 3.10 kilonewtons per meter as a wind draft, and also 1.3 kilonewtons per meter as a wind draft for the last part. Also, we will need to look at the benefit that we have in Rfem 6, that it was the area that we had on our gable supports, where we will calculate our load distribution according to DIN 1991-1-4, section 7.2.2 for vertical walls of buildings with rectangular floor plan, which will give us a load magnitude of 0.52 kilonewtons per square meters. To continue with the input of this load, I firstly need to go in our program again, and I will select here a new load case, which I will name it wind in plus X direction. As an action category, I don't need snow category anymore, but I will choose wind here, and I will press OK. Just like we did for the drifted snow load, I will need to use now a new member set load. As a load distribution, I don't need uniform anymore, but I need varying. Of course, the first thing to do is to know how long is one of our trusses. To do that in Rfem 6, we have a lot of ways. We can first, or which is also the simplest way, to go here at the table to the member sets and look at the length of each member set, which is 23.2. Or we can select one of the member sets and then say that I want to edit this member set. And then here we will have the length, which will be 23.2. We can continue with the input of our load. As I said, we need a varying load. In local coordinate system for the load to be perpendicular to our trusses, we will start here at 0 with the value of 1.3 kilonewton, 5.8, also with a value of 1.3 kilonewton. Here we will have our wind draft. And here it will be the end of our truss. The next thing to do is to select the member sets where we need to apply our load. We can say here apply and next, and then we can see that our load has been generated. The next thing to do is to apply the same load with the half of the values for the gable supports, and I can just change the values here by adding 0.65, also 6.65, 1. As always, we need to select our member sets and then continue with OK. Here we have our load that has been generated. Now we continue with the load on our surface, which is a load distribution area. As we saw in our PowerPoint, we will have a load magnitude of 0.52 kilonewtons per square meters, of course, as a load direction global in Y on true area. We will select both of the areas and then continue with OK. We can imagine a bit how our wind is going to go in X direction, which tell us that the load on the surface here is on the wrong direction. To change that, I will just add a minus here, which I will confirm it with OK. And this would be our load for the wind in the X direction. To look at our benefit that we receive from the load distribution area, we will need to go to the display navigator and search here for surfaces. We will have a small menu that says loads from distribution surface. If we check this, we will see the distributed loads, where we see that there are triangular loads and also trapezoidal loads that comes from the roof structure. Back in the days, we used to input all of these loads like manually because there wasn't a faster way. But nowadays, there is a way faster way and also an easier way that we have with the load distribution area. So we also use it. The next thing to do is to apply the wind load in the Y direction, like in the other direction. To do that, I will first would like to go again on our PowerPoint. For this type of load, there is nothing in the standards, or I didn't find anything, but in principle for gable and trough roofs, according to DIN 1991-1-4, section 7.2.5, there are CP values for wind in the longitudinal direction, also in Y direction. I calculated an average of 0.7 multiplied with the peak pressure and also with the influence width, and applied it over the entire length of our truss, which is a load equal to 2.3 kilonewtons per meter as a wind draft. Just like we saw it for the other type of the wind, we also need to look here at the wind load in on the area. in Y direction, which would be according to DIN 1991-1-4, section 7.2.2 for vertical walls of buildings with rectangular floor plan. We'll have here as the first area, which I named it with D because this is also how it's described in the standards, where we see a CP value of 0.7 and we have a load magnitude of 0.46 kilonewtons per square meter. And also the next, which is also the second area, I named it also with S, where we will have the 0.3 as a CP value, where here would be the wind draft on the area. To continue with this wind load, I will go again to our program. And just like we did it for the last times, I need to add here a new load case, which I will name wind in plus Y. As an action category, I don't need to change it. It's fine. And I can just proceed with OK. And start inputting our load. I need a new member set load, just like always, but this time I don't need anymore a load distribution varying, but a uniform. And I will just put our value that we saw in the PowerPoint, which was 2.3 kilonewtons as the wind draft. And I need to select all our trusses that we need this load to. We can select here apply and next. We can see that our load has been generated, and then we can change here the value for the half of it in the Gable support part, which will be 1.15 kilonewtons per meters. Just like always, we select the place where we want our load to be and then proceed with OK. Also, not forget, also for this part, we need a coordinate system as local for our load to be perpendicular, like with a 90 degrees angle to our truss. This was the load in our on our trusses. Now we need the load on the surface areas, where I need a new surface load. Just like we saw it from the PowerPoint, first for the first area, I need a load of 0.46 kilonewtons per square meters, of course with the load direction global in Y on true area. And then I just need to select the load, the first load, continue with OK, apply and next, check if the load is being generated, and then apply the next load, which is 0.20 kilonewtons per square meters. I'll proceed here with OK, and that's how I'll be done with the load in Y direction. The next thing to do is to imply the imperfections, where I will go to the imperfection and select here new imperfection case. I can just name it imperfections. Of course, you can name it as you wish. And here I need to be sure that my imperfections are set active, and then continue with OK. I will need a new member set imperfection, of course, as an initial bow, manually relative, which will be with a value of 1/400th. As an imperfection direction, I will need to choose a local in Y and then select all the members that we have. Of course, we could have done it also by setting it manually, just by typing 1 until 6, but this way it's easy to do. We see that now our imperfections have been set. The last thing to do for the load input and the combinations is to apply a bracing for the tension rods, which of course it will be easier for me if I could just see the tension rods for me to be like easier to apply the bracing. To do that, we have a lot of ways in Rfem 6. One way could be just to press on the member representative, which I can select every one of them, and then say here visibility by selected objects for me just to be able to see just them. Or I can go to the visibilities and activate them and say by members, members by section, and choose here the round section. Our bracing belongs to the dead load and roof structure, and here I need to set a new member load, where as a load type I will need to add an initial pre-stress, which will be 0.5 kilonewtons, and assign it to all the members that I want it to be assigned to. Check if everyone is selected. It looks good, and then I can proceed with OK. Now we are done with our load input and the combinations. So we can start with the design of the timber components. To do that, I will need to go again to my PowerPoint. For the design of the timber components, we will also be looking at the stability control according to proof 6.3.2, which is the proof for the flexural buckling, and also as looking at the lateral torsional buckling, which will be the proof 6.3.3. To continue, I would just need to go again to our program and to see if also we did a mistake or something, I will calculate everything. So we can also see the deformation for every load case. And also, of course, if we made a mistake, our program will notice it and it will say that here something is wrong. Of course, because we are calculating everything, this will take a bit of more time than just calculating just one singular snow load. We have here all the deformations where we can look, and also like local deformations or strains, internal forces. We see here that we have like too much information, so we need to shorten up some things. For the design of the timber components, I don't need to look at the entire hull, but I will just look at one of our trusses. And then from this truss, I will look at the stability control. To start with it, I will just select this truss here, and I want to see just this truss for it to be more easier. First of it, we need to check if the member orientation is correct. To do that, I will need to go here to the display navigator and search here for members and say here member orientation. And we can see that our member orientation is the same way as I wanted to, like it's correct. I will take a look at our load cases, where here we have like a lot of load cases that we also will not need. Firstly, I will go to our design situation, and at our combination wizard, I will need to edit it, and here we'll have like a part that says options 2, and I will need to check here favorable permanent actions, which would be there for the lifting loads, and press OK. Looking at the load combinations, there are, for this part, there are just these 2 loads that I will be looking at. So the rest of it, we can either leave it this way, or we can just select all of them, and we can say here that I don't want to calculate them, and continue with OK. To start with the design of the timber component, we will need to edit our member set. And we will see here design properties. We will need to check and go to the design types. Here we have the effective length, where we will need to add a new effective length. And here is the menu where it gets interesting. We say to the program, I will make a stiffening disc on top of it, and then I just need to prove the buckling around the major axis. So the flexural buckling around the minor axis and the lateral torsional buckling, we don't need to look at them for now. If we go to the menu nodal supports and effective length, we will see that here we have an effective length factor, which according to the standards, we need to calculate it. Of course, I calculated it before we did the webinar, and for our round arch hull, we will have an effective length factor of 1.25. We can select here with OK, and then go to the summary. We'll go to the timber design. For the stability control, we always just need to consider the ultimate limit state. The rest, I don't need to look at them because this would be deflection, and we don't need the serviceability limit state. Of course, I also don't need to calculate every single truss, but just this truss that I have here. So I will go to the menu Objects to Design and deactivate everything. And here I will search for the member set, where I will go at the selected objects and just select our member set. Now I will proceed with the calculating of our member sets. Where we can see that every proof is successfully achieved. Therefore, we will receive here a warning that says that the equivalent bar method cannot be used as standard, and that is why I can say I can stiffen it, and then all I have to do is to check the flexural buckling around the major axis. For that, there is a proof according to German standards, which is the proof 6.3.2, which can also be used for the equivalent bar method, which would be the proof here. If we look more into it, we can see here that we will have at the design check values, we'll have here the equivalent member length, where we will have a length of 28.9 meters, which, if we remember, we had a true length of 23.2 meters. That means that our member has now extended from 23.2 to 28.9 meters, which is in the factor of 1.25. If we try to use the value of 1, the value will still meet the requirements. However, it's not correct according to the standards. To see that, we can also go again to the member set dialog and go there to design types. And here we will continue with an effective length factor of 1. As I said, the proofs will always be like successfully achieved, but that is not correct according to the standards. Therefore, I'm using the equivalent bar method. That means I have to assume that it's braced and enter the 1.25 as an effective length factor. Normally, we don't have formwork, but rather compression supports or purlins that act here in this side. And we want to look at these for disability. Therefore, we have with our Rfem 6, we have the option of using the eigenvalue method and thus examining proof, which is also like the proof for the lateral torsional buckling. To continue with that, we go to the same dialog again, and by editing our member set, design types, and then here we say we don't need the flexural buckling around the major axis, but the lateral torsional buckling with the eigenvalue method. If we don't enter anything here, it will be calculated as an unstiffened beam. We can try it out, say here OK, and then calculate. We can see here that every proof is successfully achieved, which we will have also the proof 6.3.3, which is the proof for lateral and torsional buckling. Of course, in the reality, we cannot build our hull this way, but we can show our bending picture. To bring our model more closer to the reality, we will need to go again to our member set dialog. Probably if I show it this way, it will be also easier for you to understand what I want to explain. Here I will select the intermediate nodes, and we also saw that from the beginning we have 5 intermediate nodes, so I will add 5 of them. The nodes will be there for us to make like supports which will imitate the purlins that will be here, which will bring our model and also our truss here closer to the reality. We will say here that they are hauled in Y direction. And in this way, we can also imagine that here they will imitate the purlins. We can press here OK. And then calculate again our member set, where we will see that every proof is successfully achieved. Also with Rfem 6, we have the possibility to do something really fine to bring our model even closer to the reality, which will be at the supports where they imitate our purlins. Of course, the purlins will not be set here, but on the top of it. So we have the possibility with the Rfem 6 to select an eccentricity type, which I can choose, for example, at upper flange. At here, if we look at this support, we can say that this support, when I pick the eccentricity type as at upper flange, it will go up a bit, which it will imitate even better the purlins that will be here. For this, I can do the same thing for all the supports that imitate the purlins. To do that, I can just press the Shift taste and edit all of them at the same time. And say here for all of them at upper flange, where we can see that every single support is like a bit more up, and press OK. We can also calculate it again and show our proofs, which are, of course, are successfully achieved. And by this way, we have also our model. We brought our model closer to the reality. If we will look at the proof 6.3.3, we will see that here is the proof there we can, where alpha crit is determined, which will be the calculation here. That was all from my side. I hope it was not so long and you could understood everything. Andreas, now it's your time again. Thank you.
Thank you, Benarald, for the presentation. I have an additional hint. Yeah, just register for our online courses, the Rfem 6 course, that's a course for beginners, the Eurocode 2 course, for the concrete design, Eurocode 3 for the steel design, Eurocode 5 for the timber design, and there are also course packages available. More information and prices can you get when you scan the QR codes in the middle, or you can press the button with the links. You can download the slides and also the record. You can watch the recording and download the showed model of today from a website. You get a link to the website in the next days via email. Yeah, okay. Then I have another hint for you. I switched to our website. Quite new is the Dlubal community. You can join the community. You can ask questions there, and they will be answered by our experts or by other members of the community. You will get also the newest information of our software. Feel free to press that button and register for the community. Okay, that's also all from my side. I thank you for your attention. Thank you, Benarald, for the presentation. Thank you, Gerhard, for your help by answering the questions. I wish all a nice rest of the day. Bye-bye.